of an ancient age of coal, pointing instead to coal's recent formation, geologically speaking. To explain the halos requires that at one time, water-saturated logs were buried in what are now considered to be several different geologic formations: the Eocene, Jurassic, and Triassic. Later, uranium solutions infiltrated those water-saturated logs, and uranium decay products, radioactivity, was collected at tiny sites in each of those logs. That radioactivity decayed over the next several months to a half year, ejecting particles and producing spherical radiation-damaged regions, halos around those tiny sites. In cross-section, they appear to be circular. They were formed by the decay of secondary polonium, derived from the decay of uranium. Then there was a compression event. Something applied pressure to the top of all these formations. The logs were compressed, and when the logs were compressed, the halos were compressed. This brings us to an important point. We know that these logs had not turned to coal at the time the compression occurred. Here's a piece of coal. Coal doesn't compress. It shatters, as we can easily see. All the information we've seen thus far would indicate that these events were simultaneous in all these geologic formations. But there is even more evidence of that. When uranium invaded the wood, it left some of its decay product since the time that it invaded the wood. I've measured both the amount of uranium in these coalified logs and also the amount of lead, the decay product. On the assumption that the decay of uranium to lead has been uniform, it's an assumption we'll discuss later, we arrive at the conclusion that all these logs were buried together quite recently. How recently? In 1976, I published my results of the studies on these logs in the October 15, 1976 issue of Science. Here's what I said in this report. Such extraordinary values, referring to these lead-uranium ratios, admit the possibility that both the initial uranium infiltration and coalification could possibly have occurred within the past several thousand years. In other words, I was suggesting that coal could form very rapidly, geologically speaking. It contradicted the conventional way in which people have thought about the formation of coal. What was the reaction of the scientific community to this new data? I received a letter from Professor Raphael Kazman of Louisiana State University several months later, January 27, 1977. Dear Dr. Gentry, I have been patiently scanning the letters section of Science since the publication by you and your colleagues of your findings on radio halos. The silence is deafening. I think it can be interpreted as stunned silence. Your results will not greatly trouble the engineer, but the impact on the science of geology in possibly changing the accepted views as to the duration of geologic time will be felt for many years. Very truly yours, Raphael Kazman. Soon thereafter, Professor Kazman organized a symposium. It was entitled, It's About Time, 4.5 billion years. Is the Earth really 4.5 billion years old? When the results of the symposium were written up and published in the September 1978 issue of GeoTimes, here's what was said. However, since the deposits from which the coalified wood was obtained are considered to be at least of Cretaceous age and possibly of Jurassic or Triassic age, the ratio between uranium-238 and lead-206 should be low. Instead, some such halos have been found with uranium-lead ratios ranging from about 2,200 to over 64,000. If isotope ratios are to be used as a basis for geologic dating, then presently accepted ages may be too high by a factor of 10,000, admitting the possibility that the ages of the formation are to be measured in millennia. Translated, that means several thousand years for the formation of coal and all of those geologic formations. This information has remained unchallenged and unrefuted in the open scientific literature since it was published in 1976. We are therefore entitled to draw some rather firm conclusions about the data. Geologists have assumed the Eocene was about 60 million years ago, the Cretaceous about 110 million years ago, the Jurassic 160 million years ago, and the Triassic 225 million years ago. But the results that we presented contradict that information. It's showing instead the simultaneous burial of all these formations about several thousand years ago. These results pertain to the origin and age of coal wherever it is found.
Catherine Hill Bay, Australia. Not far from this coastal area near Flat Rocks Point is an object of extreme geological interest, an ancient tree. The fossilized remains of this tree can be seen extending through over 12 feet of sedimentary layers between two coal seams located here. Years ago, when a mining company excavated the layers exposing the tree, the bottom of the tree could be seen extending down to the lower coal seam. Since that time, the lower part of the tree has broken off. Even now, in its reduced length, the tree extends through layers geologists normally theorize to have taken hundreds of thousands of years to accumulate. But these layers could not have taken long ages to accumulate because the tree would have rotted long before the sediments would have had time to accumulate around it. Rather, this tree is mute testimony to its catastrophic burial by at least two sequences of volcanic ash deposits. As the evidence indicates, the tree was probably buried in a series of closely spaced volcanic ash flows, perhaps similar to the catastrophic burial of thousands of trees at Mount St. Helens in Washington State.
But if coal did form rapidly, we expect to find places where geologists have encountered extreme difficulties in explaining its origin by slow accumulation of vegetation. So let's take a closer look at the evidence for coal formation as it occurs in the spectacular Powder River Basin in Wyoming and Montana.
The Amax Eagle Butte open pit mine near Gillette, Wyoming exposes the vast coal reserves made visible by the strip mining methods used here. The Eagle Butte mine boasts of coal layers or seams with thicknesses ranging up to 120 feet. Eagle Butte mine is part of a much larger coal-rich area known as the Powder River Basin. This gigantic 10,000 square mile reserve, situated between the Black Hills of South Dakota on the east and the Bighorn Mountains on the west, extends northward to the Yellowstone River in Montana and southward to Casper, Wyoming. The immensity of the Powder River Basin coal deposits has attracted the attention of geologists for decades. Such interest was documented in the May 1993 issue of Earth magazine. The article, Powder River Coal, Geologic Enigma, Environmental Dilemma, included these statements. Powder River's coal seams run remarkably thick and unsullied by other material. Usually, unwanted sediment such as clay washes over a deposit before coal seams can get very thick. But Powder River coal is packed in immense strips, some more than 200 feet thick. These seams stretch vast distances up and down the basin. They're hundreds of miles long. They're 50 miles wide, says James McClurg, a geologist at the University of Wyoming. They're not little pods of an acre or two. They're immense things. McClurg, who studied the basin for more than a decade, says no other place in the world has as many seams 50 feet or more thick.